Hi, in this video, we want to take a look at Bayesian confirmation factor analysis. All right, so remember, if we're doing factor analysis, we believe that there are latent variables, hidden variables, variables that we can't actually see that are driving variables that we can observe and measure. All right, so what we want to do, we want to use the observable, measurable variables to get an inference about the variables we can't see. Now in confirmation analysis, confirmation factor analysis, what we're doing is we are going through and we already have a model. And I want to, after I've collected some data, I want to go, hey, does this data fit my model? Does my model fit my data? And see, does it look like we have a good model with our data? Okay, well now let's take this a little bit further. Let's say that in addition to having a model, I actually have prior beliefs about that model to the point where I have a Bayesian point of view, Bayesian priors on this factor analysis model. All right, so now what we want to do in this situation, we actually have a model and we have a pretty good description of what's going on. So what we want to do is just take our data and go, hey, does this look good? Does this data confirm the model that we already believe to be correct? Now, some things about Bayesian statistics. Remember, there's definite trade-offs with this. Bayesian statistics give very complete information about what's going on because you have all these distributions. It's a very, very comprehensive view of what's happening, but there's a catch, and these catches are non-consequential. Okay, so first and foremost, it takes a long time to run these. Just let you know, for this video, I ran this, I went and took a walk around the block and came back. And I took a long walk and it fortunately had finished, but it was taking a while. And I would have been twiddling my thumbs if I would have been sitting and waiting for it to run. Another disadvantage is that if we pick a poor prior or we tinker with things, we can get a screwed up model pretty easily. And another disadvantage is that because of the ability to basically choose the output by manipulating priors, a lot of classically trained statisticians do not trust Bayesian statistics. So we just need to be aware of it. We need to know about it and make choices for your situation as best. I would really like to use Bayesian statistics. For me, when I have very little data, that's my preferred time to use that. Because if I have a lot of data, I tend to not even need the prior to get the information I'm looking for. So I'm not going to even bother with the additional computations. Okay, so what's going on with Bayesian statistics is that we believe that there is like a distribution to the actual parameters. And so since there are, there's a distribution to them, we get more information off of it once we have that distribution. So we have an initial belief. That initial belief is called our prior distribution. And so without observing any data, I actually have distributions of all the parameters. Now, once I get data and I incorporate my prior beliefs with my data, I get new distributions, and those are called our posterior distributions. All right, so let's run through the example. And this is taken from, it's modified from modern psychometrics with R. And this is by Mayer. And there's a GitHub page for the code. And so we're going to set the options to 2 so that we don't get blasted in the face by numbers. And we're going to use the Berg data set once again for factor analysis. All right, so we want to use the B-Levin package. So it's Bayesian latent variable analysis. And let's see what happens as we run this. So once I pull up the package, all right, a lot of things happen. Anytime you're dealing with Monte Carlo Markov chains in R, a lot of stuff starts coming along for the ride. And this is no exception. So whenever you're using Bayesian statistics, unless you're doing a very, very narrow range of problems using conjugate priors, you're going to be using Monte Carlo Markov chains. And because of that, a lot of stuff comes out. So you'll notice that the RC++ package is coming along for the ride. RC++ parallel is also. And with that, we get some functions that name-wise are overlapping with what we already have. And it gives us this notification that if I was running a multi-core machine, I would want to use the future package to set up the multi-processes. But I'm running on a pretty weak machine for this, so I didn't even bother, because it just, I don't think the additional overhead aspect for parallel programming will be worth it for this particular machine. If I was running on a more substantial machine, I would definitely be using some parallel processing. All right, so now our prior distribution are our beliefs about the distribution of parameters before we get started with data. Well, let's go ahead and take a look at them. Here are the default priors, and in the package, we can go ahead and we can change any of these as much as we want. We can change, like conceptually, we can change it to any distribution that we want, as long as it matches in terms of discrete continuous. Now, the new parameter is normal, 0, 32. Then alpha is normal also. Lambda is normal. Beta is normal. And then when we get to theta and psi for the standard deviation, these are gamma distributions. All right, so for gamma, remember that has a non-negative support for the distribution, and standard deviations cannot be negative, so this makes sense. Now for rho, this is the beta 1, 1, which is the uniform distribution. Now here for the correlation matrices, we have Wishart. And then for tau, we have normal distribution. And then delta, once again, we have a standard deviation distribution for gamma. Okay, so to get biased results with a prior, what you do is you shrink down that variance to super, super small, and you set the central tendency at a value that you want it to be. And that's how you can tinker with Bayesian statistics. All right, so what is the exact opposite of doing that? The exact opposite of doing that is going with big variance. So if you don't know and you're doing Bayesian statistics, go with a very big prior distribution, and you know you're not biased in your results. All right, so now let's go ahead and compute the Bayesian confirmatory factor analysis model. So this is very similar to what's in the Levon package, but we slap a B in there. Boom, and we got it. All right, so we're going to say that there is a global prejudice that has indicators of EP, HP, DP, SP, and we're going to do a burn-in of 2000. All right, so what this is doing is that when it does the Monte Carlo Markov chain, it's going to randomly generate observations. To make sure that we get a distribution we can trust, it's going to go through 2000 iterations, but not actually use those. After 2000, it's going to kick off the ones that we're going to keep, which are going to be 10,000. And it's going to do this 3 separate times with different random number generators. And so we do this so that we get a full complete distribution, and we can make sure that, like, the burn-in is very important. That's if we do not have sufficient burn-in value, the number of iterations that we're going to actually waste, then we can't trust the distribution. The burn-in is super important. Now, when I do this, it goes ahead and gives me some feedback on what's going on. And, so here it tells me which chain it's working on. And, it goes through some processes. The iterations let us know, like, where it is in the process. So we know that there's 2000 burn-in and 10,000 that we're keeping. So we can see, like, which iteration it is, every few, to kind of give us an idea of what's happening. And you'll notice that the first 2000 are warm-ups. And then when it reaches 2001, that's when it's actually kicking off to keep it. Now it gives us indication of how long it takes. So you'll notice that that was, a good amount of time right there. I would not want to sit around waiting for that, so I didn't. Does the same thing for chain 2 and chain 3. So now we've got, a good amount of data. So let's go ahead and inspect those results, because we want to see what's going on. All right. When I get my output, I get distributions. All right, so here I have distributions, not like confidence intervals. So with when I'm talking about an interval in Bayesian statistics, that's a credible interval. It's not, so the interpretation is different. Operationally, people look at it the same way as a credible interval and a confidence interval. There's technically a difference, but in a lot of ways we treat them the same operationally. All right, so we want our Bayesian posterior predictive p-value to be close to 0.5. That way it's not too far left or too far right in terms of like a, too extreme of values. We want our 95% highest posterior density interval to not contain 0. And we want our potential scale reduction factor to be less than 1.2. All right, so let's take a look. All right, so my posterior predictive p-value is 0.56. All right, I'm satisfied with that. Now let's go ahead and look at our coefficients. So remember, all right, so something about this, if you remember the formula had 4 indicators, but I've only got 3 printed here. The first one is rescaled to be 1. All right, so if that's automatically 1, then everything else that follows, it is going to have variation, but the first one is always going to be 1. It's not going to be meaningful to talk about its distribution if it's always 1. And so here's the estimated coefficients using the density. So that's either the mode or the median or the mean. And I honestly don't know from this package. It's just a central tendency, and I'm going to accept it as is. Now here, these are the intercept terms. And then here, these are our covariance terms. And so remember, like in regular regression, you had to have constant covariance in terms of your predictor variable. Here we're saying we don't have that, but that's okay because we have a very comprehensive understanding of the model. So it's not a big drawback to not have that hypothesis. And that hypothesis really is not important for this usage. All right, so let's look at the summary. Here are the number of observations in the data. Got 1 missing pattern. We already saw this one. And we have our marginal log likelihood, pretty small, but that's normal that's typical when we have smaller, or when we have more dimensions, the log likelihood tends to be very, very small. And you'll see that the first loading is going to be a 1. And then here we have our estimates of the coefficient and the standard deviation. And here's the prior. Now here we can take our intercepts. We'll get similar values. And here are the terms for our variance and covariances down here. All right, so now let's look at the diagnostic plots. All right, I want to see that each of the chain has gone flat. And so I'm looking at this, and I think it's 2 is in the middle here. That looks kind of weird, but it looks flat. If I see a curve or I see stairs, then I have concerns. It's completely flat. So I'm okay with it for each of the chains. And these are for the kept values also. So this is after the burn-in has ended. Now let's go ahead and look at the autocorrelation function. So if I have substantial autocorrelation between consecutive observations or lagged observations, then that's a sign that I'm not really, I haven't reached the point in the burn-in that I can trust the output. Here, these are pretty flat. There's a little bit of bumpage here, but I'm going to call that okay, because real models do not work out perfectly like they do in the textbooks. And then I want to take a look at the values we get for these coefficients and look at scatter plots between them for the loadings. And we can see that there is kind of an ellipsoid shape, stronger ellipsoid ellipse shape. But I mean, these look a lot like clouds. So I'm okay with this. And here on the diagonal, we get histograms of the loading coefficients. So I'm satisfied with this. So from what we have here, I am concluding that this is probably a pretty good model. All right, well, that's all I've got for you. Take care and goodbye.